Hello everyone, today I will be presenting entropic forces in Brownian motion. So, what is Brownian motion? Brownian motion occurs if we have a particle like this yellow particle here in the figure on the left that is submerged in a fluid. And so these fluid particles are moving around and they occasionally bump into the yellow particle, exchange their momentum, and cause this yellow particle to undergo random sporadic motion. And this is generally a very complicated process. So a way we can simplify it is through a random walk, also known as a drunkard's walk. So if you look in the figure on the left, what a random walk is, it's when we can model it as a person taking steps in completely random directions, and they trace out some sort of path as a result of that. And so if we analyze this in 1D, we can look at a single random walk position path. And so you can see they go up, they go down, they go up, they go down. And it's not very interesting, one random walk by itself. But when we get a collection of random walks together, that's when we start to examine very interesting behavior. As you can see on the figure on the right here, it seems like these random walks are encased in some sort of envelope. And this envelope seems like a growing normal distribution as a function of time, or an expanding normal distribution as a function of time. And so we can examine the time evolution of random walks. So consider we have a bunch of random walkers aligned at the origin initially, and we just let them walk away. And what they end up doing is diffusing away from the origin to diffusive equilibrium. And so as we predicted, we get a Gaussian probability distribution that models what we see in the animation, and it is a result of, or a solution of, the diffusion equation. And so what happens if we plot the RMS displacement, or the standard deviation as a function of time? We get that the RMS displacement goes by the square root of time, given by this formula here, and by the graph. But if we analyze this as a position versus time graph of an ordinary Newtonian particle, like from Newtonian physics, what we could see is we could say, hey, this graph has concavity, meaning that we have a non-zero second derivative in x. So this implies there must be an acceleration. But we also know by Newton's second law that F equals ma. So if we have a non-zero a, then we better have a non-zero F. So what we can conclude, it's as if there's a macroscopic force pulling the random walkers away from the origin. And this mysterious macroscopic force is called the entropic force. And it goes by -1 / distance cubed. RMS distance cubed. And if we plot the time evolution of entropy, we see that we start from very low entropy because all the walkers are lined up at the origin. And then after a long time, everyone occupies their own state, and they reach this maximum. And so what this entropic force is trying to do, it's trying to pull all of these walkers away from the origin such that we can maximize entropy, also known as reaching diffusive equilibrium. So in conclusion, we can use this entropic force entropy maximization approach to solve other Brownian motion and random walk problems without invoking a central limit theorem process.